Yeah, so maybe to get the discussion started. So yeah, we heard talks with very different topics, like a bit more technical topics, like how to plan with robots, and then Janette's talk was a bit more high level, like what role language plays. So maybe it would be interesting to get your insights. Like in the end, we want to use this on robots. So how can we actually build the bridge between these two worlds, like the very maybe more low level planning and execution on the robot, and then the understanding of humans? So what do you think are the gaps? Like what is still missing for these robots to be helpful for humans and to understand us and to translate basically our high level instructions into stuff that the planners can work with, the motion planning, the task planning, and so on. Yeah, I don't know who wants to start. Maybe John Juan.
Yeah, sure, I can start. So I think, so of course, there are many gaps. So one of the gaps that I personally think is important is how robots can actually understand human instructions in a specific grounded and physical and social context. So one example that I really have is, so suppose that the human is trying to cook something, and then the person might be doing some of the the manipulation inside the kitchen, and if the human asks the robot, okay, can you bring that knife? So if you think about this instruction, it's inherently very ambiguous because there are many knives in this environment, and then depending on what's the task that the robot thinks the human is doing, the robot should pick up the correct type of knife, right? So right now, most of the system that we currently have is given the instruction, we just directly literally translate that into some representation, and the task and motion planner, for example, can take in. So I think this is definitely a limitation of the current system. So this is related. So going one step higher level, I think it's very interesting to think about the problem of how human can actually specify their goals to the robot, right? So in the community, we have been investigating very different type of specifications. We have symbolic programs in the classical planning literature. And nowadays, we in favor of those kind of language. But again, understanding language in context is really important. And some of the people have also thinking about, showing demonstrations to them, or, showing the image for them, basically thinking about what should be the interface between the human and the robot. I think that's pretty important.
Great, thanks. Maybe Sharan, you can give your perspective.
Okay, yeah, so I guess the question is about how we can actually use language or language models in robots. I think that the link part of like grounding is really like clearly we see that as a community, it is the limitation right now. And I remember when we just started using language in robots or language model in robots, I got a lot of questions about because I work on manipulation, and there are just so many things that we don't describe in language in manipulation, right? The material of the object and how you actually subtly like push objects in order to achieve particular goal. So I think there's a lot of questions, like open questions that need to be answered, like how we actually use language or like the structure of language to support robots. And I also see there's a lot of promising directions, but by like just carefully think about what is things that language model are good at, what are the things that, like for example, the physical understanding is just like, maybe they're not good at, but we have other set of tools that can help, right? So we have motion planning that can actually be very useful to be used by the language model to kind of plan out the low-level actions. We have physics simulators that can help us to understand the low-level interactions between objects. So I guess maybe the answer, or maybe one of the answer, is to think about how we can combine different tools, not just language, and also a lot of things that we already know how to do together to make a useful and functioning robot system. Yeah.
Okay, thanks a lot. And maybe Janet, your perspective more from the language side, like how would we connect this more really to the physical world? Like in the end, if the robot needs to execute something, it needs X, Y, Z coordinates. Like how do we make this link?
Yeah, so one of the things would be for the robot to know when it, or to have a good estimate of when it actually thinks it's understood. which knife, and when is it ambiguous, and to be able to query back specifically for the part of the task or the comment that it doesn't understand. So I think it's possible at the moment for the robot to repeat back what it's intending to do, but from a human point of view, that's not something we tend to do very often, because so much of it is already understood. You can't give a complete description, because a complete description is just multi-level, multi-layered. You always try and work out what's the most important thing, where the focus of attention should be. So one is to be able to work out the ambiguity. What I would add from the language point of view is it's not just the ambiguity of which knife, but also there needs to be ambiguity around the task. Does the person want the knife handed to them or placed near them? Is it handled first? Is it on the table? There are some things where previous experience might have taught the robot how to manage, but if you've ever been around a young child trying to do a task, you know that describing tasks is actually quite tough as well. And so there's a lot of ambiguity in that. How we can actually use language to refine that would probably be useful as well.
Yeah, I agree. So I'd like to open up for questions also from the audience, if there is anything that you would like to ask our speakers.
Maybe I could chip in here. I think this kind of relates to what you were talking about already in terms of being able to explain ambiguities and so on. Sharan, you explicitly talked about failures and how to identify failures and all these kinds of things in the work that you're doing. How does this play into the explainability part in terms of the representation that you use and deciding what pieces of information to share when there's a failure?
Yeah, I think that's a really interesting question. I think failure is probably like studying failure or try to expand failure is one example of like study this question. But I recently go back to my talk, I recently kind of really like this type of representation as hierarchical. I feel because just real world has so much complexities, and then we cannot always understand all the details, and then we really need different level of abstraction in order to kind of either specify the task or express what's going on or explain what goes wrong, right? So I feel like this kind of hierarchical representation that allows us to go all the way down to the details of coordinates or sensory input or pixels or like the forces, or all the way up to the like high level concept, and also have the nice way to go up and down this hierarchy is a very practical way to kind of provide more explanation and also make it easier to understand, because you don't always need to understand the low level detail, you just need to understand the right level. Yeah.
So this is maybe a question coming from this looking back at the great success nowadays with large language models, and seeing that was in large part maybe enabled by the data that's available to do that, right? So we have, let's say, the sum of all knowledge on the internet in text form, right? And it's interesting to think about, in the talks in this session, a lot of it was about grounding, right? And all these other modalities of data that would be useful to do that. Do you have any thoughts on how we would get to having the appropriate data to do that at the, maybe at the scale that large language models have achieved?
So are you thinking about having a data set that is grounded human-robot interaction data? Is that what you're thinking?
Yes. So how do we get to that scale of grounded multimodal data that would enable similar successes to what has been achieved with pure text?
So one of the questions is it even going to be possible? Large language models work because statistically, a sample of the language generalizes the knowledge across the culture. But in a specific instance, how many specific instances of black swans? They're unique. They only ever happen once. And how many are generalizations that you can see from past experience? And so everything that you see in large language models is a successful generalization or generative. But almost every instance of life, if you go down to a fine-grained detail, is a single instance. It's a black swan. So what you're asking is, can we learn large language models for black swan events? I'm doubtful whether the episodic features of life, what did you have for breakfast? That's not the kind of thing a large language model will ever accurately be able to guess. To get right, to guess with high accuracy. Joanne, you're nodding. Are you going to add to that?
Yeah, sure. I totally agree with what we have been talking. And then I just quickly want to mention one point. I think if we think about robot learning in reality, one of the view is that you think about robot learning has two phases. The first one is you can do some learning in your robot factory, and then here and there you can get different kinds of data. You can ask human engineers to program different kind of things for the robot. As in my talk, I mentioned that there's some basic skills that you can teach the robot how to do with a large number of data. But there's also a second phase when you're trying to actually deploy the robot in, for example, household environments. And there, the robot needs to learn a lot of additional things, like, for example, the human preference is one part of it, how to ground the concept it has learned in the particular environment that is currently in is another part. So I think both the having some grounded data that can learn some important shared transferable common knowledge, and having a mechanism that can actually do some learning in the deployment time, they are both important.
I really like this question because this is something like I think about every day. It's basically like we see so much success in like NLP or vision that because of the existence of large data, we like even simple learning methods can work so well, right? And then are we like in the robotics, I think we are always asking ourselves like is when we can get to that stage and where we can get the data. And I think if you ask me this question in my different stage, I will give you a different answer. But if you today ask me, I actually feel like simulation can be a very promising way. We are making so much progress in making simulation like either looks realistic or the physics become more and more capable. I do feel like simulation, if you look at a lot of robotics work, simulation environment is actually the one that gets shared across different labs, not the real world data, not the real world setup. So I kind of feel if we're gonna have a moment that have like a big scale data that allows the robot to learn some kind of foundation model, maybe it will come from the simulation. That's my current take. Maybe I'll change my opinion later, but yeah.
So if I could add one more thing, when our robots were learning experiences, they were able to generate references to new places by taking a place and then adding a distance and direction. They could refer to places they'd never been. And that was intriguing. And then they could navigate to those places. But when we started getting more complex, it turns out that we needed to enable them to create pseudo experiences. And I think this ties into the whole simulation thing, that you need to say, this could be the case, and then create a representation from that you can reason with, but you reason with it knowing that it's uncertain, it hasn't yet been grounded. And then later on, if you do go to that place or you do have that experience and it turns out to be veridical, you can then say it's then grounded. So being able to deal with reasoning where the reasoning comes from the generative properties of your system rather than the direct experience. And it turns out there are languages that actually say this. When you say, I know this person went to the shop, the know includes the knowledge. I know because I saw them. I know because someone told me. I know because there was evidence. And the grammar itself builds in the knowledge. And I think it's possible we need to add something like this into our causal reasoning systems.
If there are no questions from the audience, just I'm going to take this chance to ask another one. So apart from vision and text, which we have lots of, as what we were talking about earlier. Robots are embodied. I think this is something we all agree. How do you then build in the representations to encompass all of the other data that's available on a robotic system? You have force torque information, you can understand texture, touch. How do you put that into your representation? Do you just kind of tack it on at the end, or is there something smarter that we can do about it? Yeah, Sharon, do you want to start?
Okay, yeah, so I think just tackle in the end is probably the current practice, although like it's clearly we can see that it has limitations because so for example, what we have been adding sound information into our representation is just like we translate into a language and the language description and then concatenate to whatever visual description we have. But as I said earlier, there's just intrinsically a lack of like words to describe, for example, tactile information or like force information. So I think in that case, we probably need to have a different representation that ideally it can be integrated naturally with language so that we don't lose the capability that's using language as a reasoning tool. But yeah, I don't think I have an answer for that, but I do feel like that is a very interesting direction to study.
Shall we go to Jiayuan?
Yeah. Okay, so I'm going to try to analyze this problem following a kind of like a very traditional, robotics modular system point of view. So let's say we have a robot, it has, the perception system, it has, state estimation system, it has planning system, and finally it has control systems, right? So I think the short answer I can kind of give is that, this kind of different modality of different multi-sensory data, they are useful in any one of them, right? So for example, when trying to derive a task level plan, you definitely need to reason about, the material property, the texture property of things sometimes, right? And when you're doing controlling, tactile sensing and maybe some audio feedback can be very important too. So I think so one of the way to think about them as a like a unified system is to think about them from the perspective of some discrete and continuous representation space, right? So we have text space or like some hierarchical, action space that basically they're kind of like discrete in some sense. Like we think about what's the next action to take, in language, for example. But in the meanwhile, we also have a lot of continuous parameters associated with all those kind of things, like robot trajectories or object physical properties of them, or even some tactile sensing of them. Right, so I think at the end, building some system for all those modules that leverage different type of sensory data is important.
Thanks. And Janet?
Yeah, so from a language point of view, there are some things that evolution has built into the system, and there are some things that language, a shared culture of language, helps us structure. So we've got some. If you think about the language itself being supervised in how a child, say, carves up space. In English, we say in April, on Thursday, at 10 o'clock. These are all time words, but in, on, and at are actually spatial prepositions. So they're really interesting. In is used with containers, it's a 3D thing. On is surfaces, that's 2D. At is 1D, that's points. So 3D, 2D, and 1D are things that we can reason about with our systems very, very commonly. You can put something on the table or on the wall. But so every culture on Earth would probably have 3D, 2D, and 1D representations. But how you choose to group them probably depends on the spatial prepositions and the way it's used. So in some cultures, on a surface and on the wall are two different terms. In other languages, they would be the same word like they are in English. And then when you map them into time, you end up with English having April being a container, Thursday being a surface, and 10 o'clock being a point in time. Again, we've got underlying conceptual representations that are probably evolutionarily ancient, but then the way you actually choose to group them is structured by language. So I think if we can look at how language can structure our concepts and then potentially create these high-level coordinate systems, that then gives us an opportunity to learn much more rapidly the instances in, an everyday environment. So I would be saying the factory is looking at getting the evolutionary systems embedded and as much of the language as you can get. And then you refine that and structure it with the language in the very small amounts of data in a home environment or in a hospital or wherever.
Yeah, thanks. I've maybe one more question. So we heard about different kinds of knowledge that the system needs to reason. So for example, in Jiayan's talk, there were like abstract models of the domain, the actions and so on, like symbolic models. But then language models, like we heard more in Sharan's talk, they have more implicit knowledge. So yeah, where do you see the best place to encode like all these preferences and experiences that robots need to learn to understand as humans? Like, would it be in the future, will we keep all these different modes of encoding and storing the knowledge, or do you see the trend more towards one or the other? And is one maybe more the source of truth and it uses the other one just as like a lookup or like an inferior storage? Like, how do you see the relation between these different knowledge storage modalities? Maybe Jiayin, do you want to start with this?
Yeah, sure. So I think my very quick answer is I would tend to believe that at the end you need an integrated system that has all those different parts. Like you can kind of like do some kind of common sense reasoning in language using large language model. And when you're trying to do, trying to actually solve some puzzles, for example, you actually probably a planner, an actual, planner is probably of better advantage there. So first of all, it depends on the task you're trying to solve, for, of course. And second of all, I think about ways that all those things are interconnected with each other, and then how they can leverage it. They can leverage the advantage of each other is an important thing. So I can give you a very concrete example. So for example, in task and motion planning, at the task level planning, a typical failure mode for those task planners is that when there are many possible actions you can take, when there are many different objects you can interact with, the task level planning is going to be very, very slow. But if you think about a large language model as a source of like common sense knowledge, it really provides you, some ways to smartly decompose the task into smaller pieces. And also it can tell you, what are the relevant objects and, operations that you can do, right? So think about, I think having an integrated system that really allows the integration with each other for different systems is it's going to be a good solution, I think.
Thanks. Janet, what do you think?
I think that was a good answer. I think the idea of having multiple different ways of integrating this information and then being able to evaluate when the information from each of the different systems is useful, reliable, fast enough, and how each of the systems might be updating each other. So all the different head direction cells that you have in different regions of the brain, if you close your eyes, the much slower ones from the vestibular system will be updating all the different areas of the brain. But then if you open your eyes, suddenly the very, very fast ones from vision will take over because it gives you much faster and more accurate information really quickly. And so I don't think we have those kinds of architectures yet where the systems themselves can evaluate how accurate they are or how fast they are or how relevant their knowledge is. But if we could begin to put in that kind of metric evaluation, then the systems themselves can start to work as a cooperative enterprise to decide between them which are useful ones, useful ways to proceed, or useful modules to choose at any one time.
Okay. Sharan?
Yeah, I think I totally agree. I think it's very hard to argue that argue against that we need multiple model. I think it's clearly that's different model, different type. We in different type scenario tasks we need different type of knowledge base and different models, and ideally they can work together. And then I think one of the interesting idea that I kind of observed lately is that if we don't constrain ourselves as like language as just natural language, but also kind of think about this programming language, for example, it's all of a sudden open up a very powerful tool of representation. It allows us to actually kind of glue different type of model together, and also allows us to call different type of method or different models very naturally. So I think using language model as like a code writer, I think that is a very powerful idea that potentially can be used for like combining different models.
Great, thanks a lot. So let's, I think we can wrap it up at this point. So let's thank again our speakers for this inspiring session.